So in this case, what I show here is essentially just the system invoking the goto operation and remembering a previous location of an object. So in this case, it's just needing to record the position of the object on the map and then to call the goto operation so that it can go back to the location of the object. As we will see, it will drive back to the location of a bottle. In this case, it already knows the location of the bottle. So this is quite simple case at the beginning. And I also show here question answering, like where is the bottle currently? And it's giving the red coordinates as an answer. So it's just encoded as an add relationship between the thing and the location it got from the map. And now it gets interesting because I ask it to explicitly see a bottle on the left side of the robot. So this is a statement which usually only appears when something is seen by the camera, either on the left or on the right of the robot. So it now needs to invoke knowledge of how to see the bottle. And here it has some background knowledge, which simply says that it should invoke the goto operation in order to see the object. To invoke the goto operation with the object in order to see it. So this is a quite simple scenario. So this is a bit like in test chamber, where it can simply use the goto operation in order to to visit a certain location on the map. And here, so it's essentially trying to get back to the bottle. And as we have seen, it was also able to get around the obstacle on the way. So this is one of its features. This is something I cannot really demonstrate in my room because there's not enough space. So this it can do. Another thing, it can also directly invoke forward, left, and right operation, which we will see here. And we also see some of the encodings here. For instance, it has this LiDAR sensor on top, which gives the robot a way to measure the distance to obstacles. And we see here currently it received event obstacle free, which means there's nothing currently close to the robot. And so we will see it invokes the forward operation in this case. And thus again, the speed depends on the distances the radar actually receives. But now we see there, now it sees there's an obstacle a bit on the left side, on the front left. And this is also reflected with this NASI statement here, which it gets from the LiDAR sensor. So it has multiple sensors. It knows the state of the gripper, whether it's open or closed. It also receives the information from the LiDAR channel, whether there's an obstacle. And it also has a vision channel, which is using the YOLO model. But the YOLO model currently does not detect an object. So currently it's not getting anything from the vision channel. So it continues. Now it will react to this obstacle on the left event. So it invokes the right operation. We can also see here the statement it used to make the decision. To derive the subcore, essentially to invoke the decision. So it now invoked the right operation, and let's see what it perceives now. There's no obstacle currently, and the gripper is still open. And since there's no obstacle, it just continues with forward operation, and it does so a few times. And now something changes. Now we see that it sees the bottle on the left. So it now has a input from the vision channel, from the object detection model, which says there's a bottle on the left side. And so what it does now is to invoke the pick operation in order to get the mission goal achieved. Here we also see a part of the visual field on the right side. It's not perfect because the screen resolution to the robot. Maybe I can show this again. So here we see like the world from the perspective of the robot. We will see a better video of this a bit later. But what we see here is that it detects the bottle. So this is essentially visualization of the vision channel. So it now tries to grip the object, and since it has gripper feedback, it also knows whether this succeeded or not. I think this already showed last time, but last time it always failed because the camera here, if it's rotated too much to the left or too much to the right, then it will not see the middle correctly. So it will think the object is in the middle, even though it's too far to the left or to the right. But this is fixed now. So it's now trying to grab the object. The reason why it's slowly grabbing the object is that there is a feedback mechanism. There's an issue when grabbing it too quickly because it can destroy the server motor here. So it needs to take into account whether it was able to make the grip more narrow. And once it cannot make it more narrow anymore, it knows there was something which it's like a touch feedback essentially. It means it knows it has touched something, and so it knows it has successfully grabbed it. Then it lifts it up. Then it just keeps going with the mission. I think there was some obstacle there, so now it rotated to the right, and again a forward operation. And here now we see this this operation from the robot's perspective. So essentially we see what previously we couldn't see very well, how the world looks like from the camera, from the robot. As we see, we get some misdetections. Sometimes sometimes it thinks the robot arm is a cell phone. And maybe it's close enough. But this can happen, that it also detects a cell phone there, even though it's itself.
Is it YOLO, or what else you use for this object recognition?
Yes, YOLO.
Okay.
YOLO version 4. No, we see it has also correctly put it down. So this was only to test the pick and drop operation. So it's essentially like a routine to pick and drop objects. So this is from the robot's perspective. And now what I have in this example, now I thought, why not combine the two? Like now I'm sitting in front of the robot, and here we also see it from the robot's perspective, and it also sees there's a person on the left side, and because it has the map channel, it also associates the detection of the person, the visual detection, with the map coordinates. So it also remembers the person is at this location. And now we so
the map coordinate, is the map static with respect to the whole room, or for a certain area of the room?
The map is essentially updated by the LiDAR sensor. I can show like here.
Okay.
That this is a view of the simultaneous localization and mapping. So this LiDAR sensor automatically essentially the map channel automatically builds a map according to the laser scans it gets from the radar sensor. So it essentially builds an internal map of the environment. And this one, and from this map channel, it receives location. So it so in this case, it got this 500, 500, 500, 501 as a map location, and at this map location it also associates the person it has seen on the left side, so it knows that at this map location there is a person, essentially. That's what it currently does. The map channel is also, it's quite how to say it, it supports bounded size, so a bounded how to say a bounded data structure which allows it to delete order locations where it hasn't been for a while, so it can essentially operate in a way that it does not need more and more memory over time, but begins to forget like order locations where it hasn't been for a while, which is quite convenient because I want the overall system not to need more and more memory, but to work with a fixed amount of memory. This it can already do. So now when we ask it what is on the left, for instance, that it would answer like with person, because this is what it currently says on the left side. And if we let it continue with the mission, with the guard G, it will just invoke forward operation, because there's currently, if we stop it, that the grip is open currently and there is no obstacle again, so it invokes the forward operation. And now it again sees the bottle, so it picks up the bottle again. It takes a bit for it to grab it. Here it now got it. So it again tries to grab it now with using the sensor feedback. And also this pick and drop operation is also bounded, so it can only take, like if I would put the bottle further forward, it would terminate the pick operation and it would have to re-invoke it. It would then have to invoke the forward operation to get closer to the bottle, or it would have to re-invoke the pick operation. So it will always get the control back to NAS, so to have constant time operations.
How does the sorry, I have a question. How does the picker feedback work if the operation is just a single operation like pick?
It essentially it will receive a feedback event, which tells it about the state of the grip, or maybe we can see it actually. Here we go. We see that the gripper, essentially it noticed when it tried to grab the object that it cannot make the grip more narrow. So the gripper reported an event called gripper hoarding. So it knows that the grip operation was successful, because if it's not, it will just re-invoke the pick operation, or if the object is too far away, it will invoke the forward operation to move closer. But if it succeeded, like in this case, it will essentially sense that it's currently gripping something. It's like a touch sensor, so to speak.
And so that event somehow inhibits the operation.
This event,
Like stuff, like basically there's like a condition stopping the pick op. How does that work?
it's essentially the pick operation, which has like a constant time code in it, which immediately when the grabber cannot go any more narrow, it will terminate the operation and it will return this event to us.
Okay, I see. Cool.
And
This thing is pretty cool. How many sensors does it have? So it has the radar, the LiDAR.
It has a LiDAR, it has a 3D camera here, so it also can see, in principle, it can also see the distance to the objects.
Oh yeah, that is a 3D camera.
Cool. And then it has the servers, and each of the servers also has an angle sensor inside of them. So it can essentially, like I'm essentially using the angle sensor as a touch sensor. This is why it's slowly grabbing the object so that it will not destroy the server or crush the object, but it will incrementally increase the angle until it, for some reason, because it's blocked, because there's an object in the grabber, then it will notice, okay, it cannot go any more narrow, and will return with the hoarding event. And now something interesting happens because it has remembered the person. It knows the location of the person and invokes the go-to operation in order to get back to the person. And here there's currently a fixed weight in the go-to operation, but actually I should also add some feedback there. But it still gets some feedback because the observations will be different dependent on whether this succeeds or not. So in this case, because in this case it expects that there will be a person on the left side. This is what we see here. It says if we hoard the grip and we go to the person, then the person is expected to be at the left side. But this depends, of course. If for instance the person is not there anymore, it will notice that the anticipation essentially fails, that the person is not on the left side. Or if it succeeds, it will notice that there's a person on the left. Maybe we can scroll forward a bit here. So essentially, in this case, there is a person on the left side. So it invokes, so it says there's a person on the left side and invokes the drop operation. So it's like robot fetch, so to speak. So at the beginning, it saw the person, then it searched for the bottle, it found the bottle, it picked the bottle, and it remembered the location of the human, so drove back to the location of the human, then saw the human, and once it saw the human, it then invoked the drop operation. And that's essentially concludes the experiment. Maybe I can also show you the background knowledge. So we have seen multiple pieces of knowledge which it used in this experiment, like it used this obstacle avoidance behavior, like if we saw with the obstacle, with the box. So if it sees an obstacle, it knows it has to move to the left in order to not see the obstacle in front anymore. Or like actually, if it depends where the obstacle is. If it's on the left, it invokes the right operation in order to not see an obstacle. If it says the right operation, it invokes the left operation not to see it. and so on. And these 3 lines can actually also easily be learned, but it takes a few minutes. Maybe I will show this in a separate video, because it's also quite good to see that it can learn obstacle avoidance from observations. Additionally, so in this mission, it should keep driving forward, but of course, sometimes there's an obstacle, so it has at first to clear the obstacle before it can go on exploring. Additionally, it has this piece of knowledge about the goto operation, which it can invoke to directly go back to an object location in order to see the object again. So this one is some background knowledge. And additional mission knowledge it has is, if the grip is currently open and there's a bottle, then it should pick the bottle. And also, if the grip is currently holding something and there's a person on the left side, then it should drop it. But what's quite interesting is that this is all the knowledge it needs in order to explore the environment, to find a bottle, to remember where a person is, to go back to the person if it already got the bottle, and to drop the bottle at the person's location once it's there. So it's quite easy to also build alternative missions. So this is just one mission I found interesting. And of course, because it has this Nasir shell, it's also quite good for debugging purposes and also for question answering, like to ask the system what it has seen before or what it currently sees. And so it's quite convenient to have this ability. Oh yes, that's it.
It's pretty amazing. So it's those 7 lines for 7 lines of background knowledge to learn fetch.
Yeah, I agree. That's very powerful to have it operate with this Nasir statements.
Yeah, really succinct. Very nice.
Thank you.
Yeah, I think also the timing is good. We are currently working on this new proposal with the GPL team.